Okay, these are your notes for Unit 11, Objective 1, our limits review. We call it review because you actually have notes on limits already back in Unit 4, kind of around the Objective 3 mark would be where you'd want to go if you were trying to look at your previous notes. We are doing this review kind of lesson here, although we'll add a little bit of new stuff in already. But we're doing this review lesson for two reasons. One, to lay a foundation for the last two lessons of our year, Unit 11, Objective 2, Unit 11, Objective 3, as well as to foreshadow where you will start next year. Whether you go to AB or BC, Unit 1 deals with limits, as well as obviously some additional pieces. It's not just limits. And so both classes will start again at this place, moving at the different paces that we discussed in class as we were looking at what course you might want to pick for next year, looking at the differences between AB and BC. But both will start with limits, as well as what we will look at together this year with Objective 2 and Objective 3. Both of those pieces as well will show up at the beginning of next year. Okay? So coming in here for our Objective 1 limit review, a reminder of the informal definition of a limit. If f of x becomes arbitrarily close, right, which means closer and closer and closer to a unique number L as x approaches c. And so as we notate these different pieces, this x approaches c, that is shown here in our notation. That x arrow c is x approaches c, right? And then it is important that we recognize as a reminder that for a limit, that limit only exists if we approach a number from both sides, right? Meaning we're going to be, initially speaking here on a graph, tracing our graph to see what number does it look like it's going to be as we approach both sides, right? Then the limit of f of x, so limit of f of x, go ahead and circle that, limit of f of x, which is how we say this part, as x approaches c, there's that x approaches c bit again, right, x arrow c, is L. And so that's essentially how you would read this mathematical statement here, right? The limit as x approaches c of f of x, or the limit of f of x as x approaches c. Two different ways of saying that is L, equals L. And so L is, again, a reminder back from Unit 4, L is the answer, right? And that answer is what y value, so when we get a number here, say 7 is L, that 7 is a y value, the function approaches, and we would have emphasized that a bunch in Unit 4. The idea is it's approaching, right? Not necessarily what exists at a particular point, but what happens as we get closer. What does it look like it's going to be, right? So the answer is what y value the function approaches from both sides of c. Okay? And then I always like asking this question myself to kind of further clarify what that idea of a limit is we're asking ourselves when we're evaluating a limit, especially graphically, we're asking ourselves what y value does it look like? And again, emphasis on look like, not actually what is the y value of my coordinate point, but what y value does it look like my coordinate will be, right? Or some variation of that question, right? It's what y value does it look like my coordinate will be? Whether or not there's a hole there or actually a point or the point exists somewhere else, all of those are fine. You're going to learn next year that all of those pieces of the definition have everything to do with continuity, and actually we'll talk even, or we'll review, I should say, a little bit more some of our discontinuities here that we learned back in Objective 4, but you will learn kind of even more what that definition of continuity will look like next year. Okay? Okay, and then in Objective 7, we looked at what are called one-sided limits. So a reminder about our one-sided limit notation here, that when we see this limit as x approaches c of f of x, but the c has that little negative next to it, what that's saying is evaluate the limit of the function only from the left side. And so we actually pronounce this, or if we were to state this statement, this is, I'm just going to do this piece here, x approaches c from the left. And it's important that we remember that that doesn't mean that we are tracing left, like we are not moving in a leftward direction. We are tracing towards C. X is approaching C from the left, or you could say starting on the left, right? This one here with the little positive is from the right. X approaches C from the right. And again, that doesn't mean we are moving in a rightward direction. It means that we are still approaching C. X is getting closer and closer and closer and closer to C. But as we do that, we are tracing, in this instance, in this one-sided limits instance, from the right, starting on the right, moving towards C. Okay? And then removable and non-removable discontinuities, which we would have, again, have looked at back in Unit 4. Removable discontinuities, remember, are holes in the graph of x, specifically ones that are non-jumps. And then non-removable discontinuities are vertical asymptotes in the graph of f of x, or potentially jump discontinuities. Are two different types of discontinuities there, okay? And again, we'll explore more next year in both A, B, and B, C what specifically, or why specifically, a vertical asymptote is a non-removable discontinuity, a jump is a non-removable discontinuity, or a hole is a removable discontinuity, and we'll look at that some more, okay? Okay, so we have, starting this off here, a graph just to, again, kind of practice some of what we looked at. The graph side of things would have been done in Objective 7 of Unit 4, if you're wanting to go somewhere for some additional practice, Objective 7 of Unit 4. But I'm going to do a couple here, and then I'm going to recommend that you pause and try a few on your own. But I'm going to do 3 altogether just to kind of remind ourselves of what we're doing here. Okay? So starting here with A, we are approaching, the limit as x approaches -1, so we're approaching -1 from the left. Remember, that's what that little negative means. That's from the left. Okay, and so the first thing we want to do is identify, okay, well, where is x equals -1? Okay, well, x equals -1 is right here. Okay, and so I'm going to be approaching that point in time, that spot, from the left. Okay, and so the function that goes towards that line is this guy on both sides here, right? And we're, in this case, going to be doing just the one from the left. So that means I'm starting over here, and I'm tracing towards -1 from the left. And I'm asking myself as I do that, as I approach and get closer and closer and closer to -1, what y value does it look like my coordinate will be or will have? Again, whether or not there actually is a point there is another thing entirely. I don't care if there's a point there. I just care, what does it look like what my y value will be. And so as we approach -1 here from the left, it looks like my y value will be 0, because it looks like my graph's going to touch the x-axis. Okay? And so my answer is 0. And in this case, it actually does touch the x-axis. There is a point there. Okay, great. Doesn't matter. right? That has nothing to do with evaluating a limit. So you have to ignore whether there's a point, whether there's a hole, doesn't matter. What y coordinate does it look like my point will be? Okay? Okay, -1 from the right. Okay, so we're approaching the same point, -1, so that spot there, but this time from the right, so starting right of that point, so somewhere over here, and tracing towards -1, what y value does it look like I will be, or my coordinate will be? Well, it looks like my coordinate is, again, it looks like it's going to touch the x-axis, so my y coordinate would be, therefore, again, 0. And in this case, again, my y coordinate actually is 0. Woohoo! There's a point. Still doesn't matter, right? Whether or not there's a point there has no impact on whether or not the limit exists. The limit is 0. It's all about what it looks like it will be, not whether or not it is. Okay? And then as we approach -1 here, that's where we have to decide what our value is. So now we're approaching -1 from both sides. And so there are two ways you can do this. One, you can go back to your graph and you can go, okay, now I'm going to be tracing from both sides, and I'm going to be looking to see, do they touch? Is there one number, right, a unique number, one and only one? Is there one number that it looks like they're going to meet up at? If so, great, that's my limit. If it looks like from the left I'm going towards one particular y coordinate and from the right I'm going towards another particular y coordinate, well then my answer is does not exist. The limit doesn't exist because I don't have a unique number L that I'm approaching. Okay, and so if you like looking at the graph, well, then we'd be still approaching -1, this time from both sides. The question is, does it look like as I approach from both sides, they're going to meet up at the same y coordinate? What y coordinate does it look like that will be? It looks like that will be 0. And so you'd put 0. But as I mentioned earlier, there is another way to do this, right? And this is going to come in handy at the end of these notes when we're looking at piecewise functions, because you don't actually need to go back to your graph to answer this question. We already know whether or not we are approaching the same y value from both sides because I know what y value I'm approaching from the left. I'm approaching 0. I know what y value I'm approaching from the right. I'm also approaching 0. So therefore, since I'm approaching 0 from the left and 0 from the right, I would be approaching 0 from both sides, right? If this one was 2 and that one was 0, well then I wouldn't be approaching the same number. It wouldn't be a unique value of L, and so therefore my limit would not exist because it doesn't agree. I don't have the same value on both sides. Okay? Okay, I'm now going to go ahead and walk through number 2 as well, and then you can make a choice if you feel like, you know what, that's good enough, or I want to kind of try this on my own and see how I do. Well, I would recommend pausing the video and trying it on your own, and then restarting it either when you get stuck or have an answer that you are wanting to check. And that way you can even fast forward through some of the explanation if you're pretty sure you did it correctly, and you can verify that looking at the answer. Or if you wanted to, you could kind of watch through one more with 2, or maybe one with 2 for the left and then do 2 from the right and 2 overall on your own, right? But like start to make kind of that decision for yourself here. Okay? But so go ahead and pause the video if you're going to. We have the limit as x approaches 2 from the left. Okay, so first up, where's 2? Well, 2, x equals 2 is right here, so that's what I'm going to be approaching, heading towards, right? We're approaching 2 from the left, so I'm going to be starting on the left over here, going towards 2. Okay? And the question is, what y value does it look like my coordinate will be? And as I get closer and closer to 2 here, going towards 2 along that function, it looks like my y coordinate is going to be 1. It looks like I'm going to hit that point, which is at y equals 1. Now I don't, but again, one more time, that's the point. Whether or not there's a point there, or it doesn't matter. In this case, I've got a hole. Okay, cool. If there was a point there, great, I've got a point. It literally does not matter at all. So you can't focus on the point. It's what coordinate does it look like I am going to touch? What y value does it look like I will be? And so in this case, it looks like I'm going to be at 1. Okay, the limit as x approaches 2 from the right. So we're starting here and we're approaching 2 from the right. What y value does it look like we are going to become? What does it look like we're going to hit? Looks like we're going to hit the y value of -3. And so my limit as x approaches 2 from the right is -3. Okay? And then what is your two-sided limit, approaching 2 from both sides? Okay, well again, if you're looking at it graphically, you'd come up here and you'd go, okay, from the left it looks like I'm going to be 1. From the right it looks like I'm going to be -3. So therefore it doesn't agree, and so my limit therefore does not exist. I'm not meeting at one point, one unique L, like I did up here. These both met at 0, right? Then the limit existed. But if they don't meet up, then the limit doesn't exist because it doesn't agree. Okay, that would be it graphically. For those who would rather use their equations, we know also that this limit does not exist because does not agree, because from the left I know I'm approaching 1. From the right, I'm approaching -3. And so therefore, since I approach 1 from one side and -3 from the other, I can see they aren't going to be the same. 1 is not the same thing as -3. And so therefore, I do not exist because I don't agree. Okay, and then same thing, pause the video if you're going to. We've got our -2's here. Okay, so approaching -2 from the left. Okay. Approaching -2 from the left, -2 is right here. From the left is this function, and we're approaching -2, so going towards -2. Don't go this way, that's not towards -2, that's out to -infinity, right? We're going towards -2 from the left. Okay, what y value does that look like I'm going to hit? Okay, well, I'm going up to infinity. So you have two options here. One, you would have approaches infinity, or does not exist because unbounded. So approaches infinity or does not exist because unbounded. Okay, as we approach -2 from the right, so we're starting this side, approaching -2 from the right. So again, not going that way. That's going right, but that's not approaching -2. We're coming towards -2 from the right, right? And so what y value does that look like my function's going to become as I approach -2 from the right? Okay, well that's going down to -infinity. So approaches -infinity or does not exist because unbounded. Okay. Okay, and then graphically, just kind of classifying our removable and non-removable discontinuities. So remember, a removable discontinuity is a hole in the graph of x that is a non-jump. So a hole, remember, is indicated by the presence of an open dot. Okay, but for it to look like a hole graphically, it needs to be a non-jump. So you would see the function do something like that. As opposed to a non-removable discontinuity, which is a vertical asymptote, and so the graph would be doing something on either side of that vertical asymptote, something like that. Or a jump of some sort, which would be jumping, and it could be up or down, doesn't matter. There could be a hole there or a dot, again a point, sorry, doesn't matter. But you'd see that again, jump in the graph, a split in the graph, or a vertical asymptote. Okay, so removable discontinuities. As I look at this graph, if I have a removable discontinuity, I'm going to see a hole, the presence of an open circle with lines touching that hole on either side, a non-jump. And so do we see that anywhere on our graph? And nope, we don't have any of those, so we have no removable discontinuities, but we do have non-removable discontinuities, okay? Non-removable discontinuities are vertical asymptotes or jump discontinuities. And the jump discontinuity might be the new one for this unit. I don't remember if we talked about that back in Unit 4. If we did, great. It's a review, but that might be a new thing potentially for this Unit 11. So this is a specific type of non-removable discontinuity. So let's go ahead and first look for vertical asymptotes, because I know we did that in Unit 4. Where do you see our vertical asymptote? Okay, well, we have a vertical asymptote right here at x equals -2. And then we actually do have a jump discontinuity. That's why I made sure there was one in these notes. Where do you see your jump discontinuity? Okay, our jump discontinuity is right here at x equals 2. And again, we might have done jump discontinuities in Unit 4, but I don't remember. This is what a jump discontinuity looks like. Okay? Okay. So that was graphically, okay? Let's go ahead and take a look at then analytically. Analytically, we're going to start with a review of kind of what we've already done back in, again, Unit 4. And then the very end, we will be looking at a couple of new pieces with evaluating limits analytically. Okay, so evaluating the limits by the following methods, and you would use whichever one is your preferred method. I myself will always go in order here, which is I start with a direct substitution. We want to do this one first because if you can substitute in the value of c and get an answer, you get 5. Well, then you're already done. There's no reason to keep going, and you don't want to like do a factor or multiply by the conjugate or something like that and then make a mistake and now get the wrong answer, all because you did a bunch of work you don't need to do. Right? So plug in first, direct substitution, see if you get an answer. Great, you're done if you've got one. Okay? I also like doing this because it's a good chance for us to remind ourselves that if we do plug in and get a number over 0, then the limit does not exist, D and E, because it would be unbounded. That's what a vertical asymptote exhibits as. Would be an undefined. So this would be like 3 over 0 or -2 over 0. And if you get that, again, your problem's done. You don't need to factor, you don't need to multiply by a conjugate or anything like that. You've got an answer. Okay, so both of these, you are done at the end of them. Right? It is only if you plug in and get 0 over 0 that you need to do something else. So do something. And so if you're looking at it going, oh, I know I could factor that, great, factor it. Multiplying by the conjugate. Reminder that multiplying by the conjugate, I would say we frequently use in the presence of square roots, although you can multiply by the conjugate in other scenarios if you feel like that would be easy, or easier, but I'd say we usually use that within the presence of square roots. And then simplifying the complex fractions would, of course, be if you saw complex fractions, which, reminder, is through some method of multiplication, right, to simplify your complex fractions. Okay, so I've structured these so we can do, because there's kind of 2 of every version here, so that we could do one together, and then you could try one on your own for kind of, again, every version of the problem. Again, other places for you to find additional practice with these would be back in your Unit 4 notes, or if you don't have those anymore, I know they're still on my website. Go back to my website, go to Unit 4, pull up those notes. If you need extra practice, email your teacher, right? Like there's a lot of resources available to you. You just need to reach out. Okay? So let's go ahead and do number 1 together, and then number 2 will be yours. Okay, so remember, first thing, we're going to go ahead and substitute immediately to see what I get. Okay, when I take my 3 and I plug it in, I get 2 times 3 minus 4 over 3 squared minus 9, which is 6 minus 4, or 2, over 9 minus 9, or 0. Okay, which looks like the second one here. I got a number over 0, which means my limit does not exist because unbounded. Okay, and I'm done, right? If you get either of these, an answer or a number of 0, then you don't need to go any further. You're done. Okay? Okay, go ahead and pause the video, try number 2 on your own, restart it when you're ready. Okay, so plugging in my 0 up here, I get 0 squared plus 2 times 0 over 0 minus 3, which is 0 in the numerator and negative 3 in the denominator, which is an answer. What is 0 divided by negative 3? It's 0. And so you're done. You got an answer. Okay? Okay, number 3, again, let's do one together. Number 4 will be for you on your own. Okay, number 3, if I took this 2 and I plugged it in initially, I'd get 4 minus 12, which is negative 8, plus 8, which is 0. And if I plugged it in the denominator, I'd get negative 4 plus 10, which is 6, minus 6, which is 0. And when you get 0 over 0, okay, that's called indeterminate. And so then you'd be looking to do something else. And next year in calculus, you'll actually learn some other strategies on top of the ones that we're looking at here. But this is what we're going to start with, because this is what we learned back in Unit 4, which is we can factor, multiply by the conjugate, or simplify a complex fraction. In this case, these are 2 trinomials that I can pretty quickly factor. And so let's go ahead and do that. Limit as x approaches 2 of, and then what does x squared minus 6x plus 8 factor to? Okay, that factors to x minus 2, x minus 4, right? 2 numbers that multiply to positive 8 but add to negative 6 are negative 2 and negative 4. And then down here factoring this one, I myself never like when there's a negative out front. So I'm going to go ahead and factor that negative out and then see what it factors to. Okay, well, 2 numbers that multiply to 6 and add to negative 5 are negative 3 and negative 2. And so we would factor to that. Okay, and that factor then allows us to reduce our fractions, or I should say our function here, the x minus 2's will simplify, and so we have the limit as x approaches 2 of x minus 4 over negative and x minus 3. And now when we plug in our 2, we get 2 minus 4, which is negative 2, over negative 2 minus 3, which 2 minus 3 is negative 1, negative 1 is positive 1, which gives us an answer of negative 2. A reminder from back in Unit 4 that this limit notation here stays in your problem every single time you write that x function, unless you separate your work from the rest of your problem. But make sure that if you are going to write that this equals something over here, this something over here needs to not have an x in it unless there's a limit notation in front of it. It is only when the x is gone, we've plugged our number in here, like that. Right now the x is gone, we've plugged the 2 in, that the limit notation is now no longer there because we've used the limit notation. We've plugged 2 in. Okay? So again, as long as there's an x, there should be a limit notation with it. Okay? Okay, number 4. Go ahead and pause the video, give number 4 a shot, restart it when you're ready. Okay, number 4, if I plug in 4 into my numerator here, I get 16 minus 16, or 0. In my denominator, I get 16 minus 4, which is 12, minus 12, which is 0. 0 over 0 is not possible, so then I'm going to be doing something. This, to me, is a factor 1. We have a difference of 2 squares on top, which would be x minus 4, x plus 4. And a trinomial on bottom that we can factor, which would be x minus 4x plus 3. Okay, the x minus 4s therefore would simplify, and so we'd have the limit as x approaches 4 of x plus 4 over x plus 3. And then plugging our 4 in, 4 plus 4 in the numerator is 8. 4 plus 3 in the denominator is 7. And I've got my answer. Again, one more time, remember, the limit notation stays as long as you have an x. It is only once you've plugged into the x that then the limit notation goes away. Okay? Okay, number 5, doing this one together, we've got the limit as x approaches 2 of 1/3 minus 1 over x plus 1, all divided by x minus 2. If I plug 2 into my numerator here, I get 1/3 minus 1/3, which is 0. If I plug 2 in the denominator, I get 2 minus 2, which is 0. Okay, we can't have 0 over 0, and so that's when we're going to be looking at what can we do. This one here is a complex fraction, so we're going to simplify our complex fraction, and we do that, remember, by doing some sort of multiplication. Okay, so think back to Unit 4. Do you remember what we multiplied by? Okay, well, we multiplied by the greatest common denominator, whatever that was. In this case, our complex fraction is a result of what's in the numerator of our initial function here. And so the greatest common denominator is 3 times x plus 1. I'm sorry, I said greatest common. The least common denominator. Sorry. So least common denominator, 3 times x plus 1. And so we're going to be multiplying our numerator here by 3 times x plus 1. But if we multiply our numerator by 3 times x plus 1, we also have to multiply the denominator by 3 times x plus 1, because then take a look at what that means we're actually multiplying by. What that means we're actually multiplying by is 1, and multiplying by 1 doesn't actually change your function, right? I can multiply anything by 1 and it's still itself, okay? And so then multiplying here, we have the limit as x approaches 2. Okay, distributing this 3 times the quantity of x plus 1 to each of my terms. When I multiply it, so distributing here, to my first term, the 1/3, the 3's will cancel, leaving me with the x plus 1. When I multiply to my second term, the x plus 1's would cancel, leaving me with my 3. And then down here, I'm just going to write these side by side. We have the 3, the x plus 1, and the x minus 2. And I made the recommendation back in Unit 4 to not simplify anything within that denominator, as in don't FOIL, don't distribute, because what we're wanting to see is something to eventually get reduced with the numerator in some way, shape, or form. If we leave it in its factored form like this, we're able to see the different terms, and it will help us with the eventual simplification that we're hoping to find as we do our work. And so just kind of write those pieces side by side. Okay? Now, it is very tempting to make one of two mistakes. And so really quickly, before we do the next step, going back to this one, first common mistake is to forget to multiply by the denominator, or multiply to the denominator, I should say. I see this all the time where people will have this x plus 1 minus 3 in the numerator. Woohoo, you did that correctly, but then they will only have the x minus 2 in the denominator, and they won't have the 3 and the x plus 1 there. So make sure you are careful to multiply top and bottom by whatever your denominator is, in order to preserve the equality of the statement, right? So make sure you don't forget the denominator of your original function. The second common mistake is this, and this one I probably see more frequently. It's very tempting to want to simplify those x plus 1's. Unfortunately, while I can simplify this denominator x plus 1 with pretty much anything, because these terms are all multiplied, and so therefore they are all one term. Up in the numerator, this x plus 1 has a 3 being subtracted from it, meaning they aren't all one term. These are still two different terms. I need to combine these before I can do any simplification. Okay? And so make sure you are careful with that. So combining those, I don't have anything to distribute into the parentheses, so I'm just going to drop them. X plus 1 minus 3. And what is x plus 1 minus 3? Well, it's x minus 2. Actually simplifies with the x minus 2 down here. And we have the limit as x approaches 2 of 1 left over in the numerator and 3 times x plus 1 in the denominator. And now plugging in 2, we have 1 over 3 times 3, which is 9. Okay? Okay, go ahead and pause the video, give number 6 a shot, restart it when you're ready. Okay, number 6, when I plug in 0, I get 1/4 minus 1/4, which is 0 over 0. Okay, so we're going to be getting rid of our complex fraction here. What are we multiplying by? Okay, well, we're multiplying by 4 and x plus 4. Just my common denominator there. Okay? And so then doing our distribution, limit as x approaches 0. When I distribute the 4 times the quantity of x plus 4 to the 1 over x plus 4, the x plus 4's cancel, leaving me with 4. And then minus, distributing the second term, the 4's cancel, leaving me with x plus 4. In the denominator, we have the 4, the x plus 4, and the original x. Again, make sure you are not simplifying those x plus 4s. My numerator is not yet all one term. I need to distribute that negative. Which allows the 4's to cancel here, right? I've got a 4 minus 4, which is 0. Now I can simplify with my denominator. I've got an x on top and an x on bottom that can simplify, leaving me with the limit as x approaches 0 of negative 1 over 4 times x plus 4, which is, plugging in your 0, negative 1 over 4 times 4, which is negative 1 over 16. Okay. Okay, last review piece from back in Unit 4, our ones like 7 and 8. So let's do number 7 together. 8 will be yours. Okay. So if I were to plug in 3 here, I'd get root 4, which is 2, minus 2, which is 0, over 0. Okay. And so then we'd be doing one of these. Again, we multiply by the conjugate, I'd say most commonly when we see a square root or when there's a presence of a square root there. Okay. And so I'm going to be doing multiply by a conjugate here. I'm going to do a multiply by the conjugate to wherever my square root is. Whether the square root's in the numerator or the denominator actually doesn't matter, just wherever it is. And so I'm doing the conjugate of the numerator because that's where my square root is. Conjugate, remember the terms stay the same, so the root x plus 1 and the 2 are still going to be root x plus 1 and 2. The sign is going to be what changes. Because it was minus, we therefore are going to make our conjugate plus. And then if you do that to the numerator, you have to do the same thing to the denominator. Okay? The nice thing about multiplying by a conjugate is it becomes a difference of 2 squareds. The outside and the inside will always cancel. They'll always simplify with each other. It becomes just the first multiplied and the last multiplied. In your denominator here, you have your x minus 3 and your root x plus 1 plus 2. In your numerator, foiling this out, the first, so root x plus 1 times root x plus 1 is x plus 1. And then again, the outside and inside will cancel because when I multiply my outsides, I get 2 root x plus 1. My insides, I get negative 2 root x plus 1. 2 root x plus 1 minus 2 root x plus 1. They will always cancel. leaving me with my first and then my last. Negative 2 times 2 is negative 4. Okay, x plus 1 minus 4 is x minus 3. So those are going to simplify. The limit as x approaches 2 of 1 left over in the numerator. Root x plus 1 plus 2 in the denominator. And then plugging in your 2, you get 1 over, oh, I put 2, I apologize. It was 3, limit as x approaches 3. And plugging in my 3, we get root 3 plus 1, which is root 4, or 2, plus 2, which is 1/4. Again, sorry about that 3 becoming a 2 on accident. Okay? Okay, go ahead and pause the video, give number 8 a shot, restart it when you're ready. Okay, when I plug in 5 to my numerator, I get 0, and my denominator, I get root 9, which is 3, minus 3, which is 0. I can't have 0 over 0, so multiplying by our conjugate, which part of my fraction is my conjugate going to come from? Numerator or denominator? Okay, well, it's going to be the denominator. That's where the square root is. So we have our root x plus 4 and our 3, which are going to stay the same, but instead of minus, we are going to do plus. Okay? And so then rewriting this, I'm actually going to write it below. We have the limit as x approaches 5 of my numerator, which is the x minus 5, and the root x plus 4 plus 3. Denominator, again, foiling, it will always end up just being the first and the last, but I'll walk through the whole thing still. Okay, first, root x plus 4 times root x plus 4 is x plus 4. Outside, we'd have 3 root x plus 4. Inside, negative 3 root x plus 4. 3 root x plus 4 minus 3 root x plus 4 is 0. And then 3 times negative 3 is negative 9. X plus 4 minus 9 is x minus 5. And so we get the limit as x approaches 5 of root x plus 4 plus 3 all over 1, which is plugging in the 5, root 9 or 3 plus 3, which is 6, divided by 1, which is 6. Okay? Okay, so again, Unit 4, we did quite a bit of practice there. You could look at the review assignment from Unit 4, email your teachers if you have questions. Okay, but this is what I would say, besides potentially the jump discontinuity, this will be the new piece for our Unit 11 Objective 1, which is evaluating limits of piecewise functions analytically. And so we're kind of coming back full circle here. We looked at a piecewise function graphically at the very beginning of these notes. This is a type of piecewise function, right? Analytically, piecewise functions have different pieces to them. If you think back to Math 1 or Honors Math 8, depending on where you came from, you looked at how to look at an equation and know that it's piecewise, and you know that it's piecewise if you look at the equation, you see different pieces. This one here has 2, this one has 2, this one here has 3. Okay? And when it comes to evaluating limits of piecewise functions analytically, we're going to start by checking the left side limit. And we are actually going to notate that, right? We are going to write the limit as x approaches some value, whatever value it is that you are looking to assess, so we'll call it c, from the left of our function equals, and we will put our answer for that left there with your number, okay? And now, so determining which one or which function you use for the left, okay, I'm going to bring our graph back here so we can look at that. As we approached, say, 2 here from the left, and so we started over here and we approached 2 from the left, what x values were we tracing over? Okay, and then what how could you say that? What x values are we tracing over in relation to 2? Which is what I'm approaching here. What x values am I tracing over as I get closer and closer to 2? How are they connected to 2? Okay, well, these x values are less than 2, right? We're tracing over 1, 1.3, 1.5, right? 1.9, right? All the numbers less than 2, okay? And so to check your left side limit, you're going to look at the less than part of the function. Left is less, right? Okay, then we are going to check our right side limit. And we will write it. We will notate that we are checking it. Okay, well, right side then is the other side, the more than side. The ones with the R's, right? Right is more, left is less. And then you're going to ask yourself, for evaluating a two-sided limit for a piecewise function, are those two numbers we just found equivalent? Because remember, bringing back that graph, if my left was 0 and my right was 0, then my overall was also 0, because my left and my right were equivalent. However, if my left was 1 and my right was -3, then my limit didn't exist because my left and my right were not equivalent. And so that becomes the question you then ask. Are the two numbers you've written down, are they equivalent? And then I do have a little subnote here. I tried to emphasize it a bunch while we were doing the graph. I'm going to emphasize it one more time here. Remember that the limit is different than the point. Within a piecewise function, the point of a piecewise function is indicated by equals. And make sure you're careful, and I might make a note of this. The point has nothing to do with the limit. Maybe you want to put that in all caps. Nothing to do with the limit. And so if you find yourself looking at an equals statement, that is neither the limit from the left nor the limit from the right. It's not the limit at all. If you are looking at an equals, stop looking at it. It has nothing to do with the limit. It has everything to do with the point. And the point doesn't matter. A limit is all about what y value does it look like I will be, not what y value am I actually. Okay? And so we're going to demonstrate this. Because this was the new one, we aren't just going to do 2. We're going to do 4 here. My recommendation, walk through 1 with me. Then maybe pause the video, try number 10 on your own, restart it, kind of check your work, get a help if you got stuck, that kind of thing. Maybe pause the video again, do number 11 on your own. I will say number 12 is the challenge one of the 4. I still recommend you try it on your own. Don't just watch the video, but get that practice aside from the video, but I will walk through all 4. So make sure you pause the video at some point. Try a couple of these on your own. Okay? Okay, number 9, we have the limit as x approaches -1 of f of x, where f of x is given. Okay? So to evaluate the limit as x approaches -1, we need to check both of these things. The limit as x approaches -1 from the left of our function, and the limit as x approaches -1 from the right of our function. So that we can then ask, are they equivalent? Okay? So, first off, from the left, which one of these two equations is the one that goes with left? Okay? Well, this bottom one is the one that goes with left, right? X is less than -1. These are the values. If I were to graph this function, this would be the x equals 0, x equals 0.5, x equals 0.9, the ones getting closer and closer and closer to -1 from the left. And so I'm going to be using this equation here for my from the left. And so then the question becomes, well, how do we use that equation? Well, you use that equation the same way you've used all the limits that we've been practicing analytically so far. We're going to use that equation to first directly substitute. And if I get a number, great, I'm done, that's my answer. If I plug in and I get a number over 0, then great, I'm done, my answer is does not exist. like numbers 1 and 2. If I plug in and I get 0 over 0, then I'm going to be doing something else to that function that I'm looking to use. So nothing is changing about our work. Okay, we're just using it in a slightly new context here. Okay, so again, I'm using this bottom function for my from the left because that's less than. So let's go ahead and directly substitute. Take -1, plug it into my function. Okay. Okay, -1 cubed is -1. Minus 5 times -1 is plus 5, which is 4. Okay, and we're going to do a similar thing for our from the right. Okay, which function is my from the right? Okay, remember the right side limit is the more than function, which is this top function. X is greater than, more than -1. So we're going to be using this top function and plugging -1 in there. Okay, -1 squared is 1. 2 times -1 is -2. Minus 4 is -5. Okay, and then you're going to ask yourself, are they equivalent? Right, this question here, are they equivalent? Well, no, 4 and -5 are not equivalent, so therefore the limit as x approaches -1 of f of x, we aren't going to put equals anything. It doesn't equal anything. It would only equal 4 if they were both 4. It would only equal -5 if they were both -5. But because these are not equivalent, we're going to say that limit does not exist. If you want a reason, it would be because either does not agree or, actually let's make that a little bit more mathematical, because the limit as x approaches -1 from the left does not equal my limit as x approaches -1 from the right. Right? 4 does not equal -5. Okay, notice here before you pause the video and do number 10 on your own, notice that I never once addressed the equals in this inequality. Doesn't matter. Remember, one more time, what does that equals represent? That equals represents the point of the piecewise function, and that has nothing to do with the limit. So I don't care where that equals is. It could be on the top function, it could be on the bottom function, it could be its own function, it could not exist altogether, and I do not care. Equals has nothing to do with evaluating the limit. The limit is all about what the y value looks like it should be. Right? Okay, number 10. If you want to, go ahead and pause the video, try number 10 on your own, or maybe you want to do that with number 11. Take your pick. But if you're going to pause the video, do so now. Okay. Number 10, we have finding our limit as x approaches 2. Let's do 2 from the left. Excuse me. And the limit as x approaches 2 from the right. Okay. So which function, top or bottom, is the left function? Okay, remember, left is less than, so we're talking top function here. X is less than 2. Okay, so 2x plus 5. We're plugging 2 into 2x plus 5 there. Okay, well, 2 times 2 is 4, plus 5 is 9. Okay, what about the right function? Okay, well, right is more than, so x is more than or greater than 2, so the right is the bottom one. 3 times 2 squared minus 3, which is 3 times 4, 12, minus 3, which is 9. Are they equivalent? Well, yes, they are. They are both 9. So therefore, my limit as x approaches 2 of f of x up here is 9. And again, the equals, I'm not even considering it. It could not exist altogether, and it would change absolutely nothing about my thought process. I don't care where the equals is. Again, whether it's on the top or the bottom, whether it's its own function or doesn't exist at all, has no impact on our limit. Okay? Okay, pause the video, try number 11 on your own. Restart it when you're ready. Okay, number 11, the limit as x approaches 1 from the left of our function. The limit as x approaches 1 from the right of our function. Okay, so we have 3 pieces to this function. Which one of these is the limit, or is the left function? Okay, well, remember, left is less than. Okay, so which one is our less than? That's this one. X is less than 1. So we're using our top function here. We're plugging our 1 in there. 1 squared plus 3 times 1 minus 1, which is 1 plus 3 minus 1, which is 3. Okay, what about the more than? I'm sorry, what about the right? Okay, remember, right is more than, greater than. So my right function is this bottom function. Negative 2 times 1 plus 5. Negative 2 times 1 is negative 2 plus 5 is 3. Are they equivalent? Yes, they are. The limit as x approaches 1 of f of x, therefore, is 3. And again, one more time, you'll notice we didn't consider that equals to at all because, again, remember one more time, what is the equals? The equals is the point, and the point has nothing to do with the limit. In fact, if you are someone who's sitting there going, oh, you know, I might forget that. I might be tempted to use the equals one. One thing you might do when it comes to evaluating limits is find the equals and like cross that piece of it off. Make it go away. Cross off the equals. White it out if you need to. Right? Make sure the equals is never something that throws you off. It has nothing to do with the point, or it has nothing to do with the limit. So therefore, I don't care where the equals is. I will not be using it for my limit. Okay, which is, I would say, my hint for number 12. Number 12 is our challenge one of this lot. I'm going to recommend pausing the video, trying number 2 on your own, see if you can figure it out. A little bit weirder there, but I think you can get it. And then restart the video when you're ready. Okay, so then the limit as x approaches negative 2 from the left of our function. The limit as x approaches negative 2 from the right of our function. Okay, well, which one of these 2 pieces is our left? Okay, this one's what makes it a little bit challenging. Left, remember, is less than. Unfortunately, as I look at these 2, neither of those literally say less than. Okay, but one of those functions is less than, or are the values less than negative 2? Which one of these values contains, or which one of these functions contains values less than negative 2? Well, it's the does not equals. And I know that's weird, but it's where I said I gave you a little bit of hint as we finish number 11. What is this x equals 1 again? One more time. That x equals 1 is the point. The point of a piecewise function is indicated by equals. That's my point here. And the point has nothing to do with the limit. So as I'm evaluating my limit, this second function is pointless. No pun intended, right? Because obviously I recognize it is the point, but it's pointless within the context of evaluating my limit, right? And so we need to ignore that. If you are someone who's going to get distracted by the equals parts of the piecewise function, cross them off so you aren't tempted to use them. Okay, because when you do that, what are you left with? You're left with literally one function. My left is that upper function, which is 2 times negative 2 plus 3, or negative 4 plus 3. Well, what's your right then? Your more than. It's the same function, right? Your more than values are also the ones that aren't equal to negative 2. They're more than negative 2. They also aren't equal to negative 2. And so the right is going to be plugged into the same function. So A little bit funny, but are they equivalent? I certainly hope so. I plugged into the same function for both of them, so they should be equivalent. If they aren't, check your work. But so therefore, my function is x, or my limit as x approaches -2 of my function is -1. Okay, so that's your new piece here for Unit 11, Objective 1. If you have any questions or want extra practice, let your teacher know, but that's your first of your last 3 lessons.